Hello and welcome to another repair video, and today we have got a Yaesu FT-450D in for repair. Now this thing has come in, it's not transmitting, however it is receiving correctly, so we're going to go through and do some component level fault finding and hopefully we'll be able to repair it and get it going again. Okay, and if you're not familiar with these radios, this is an HF 6-meter transceiver. They cover the amateur bands, so you get from 160 meters through to 6 meters, and the receive, I think it will receive continually from something like 30 kilohertz through to 54 megahertz. They're quite feature rich. I'm not going to go through all the features here, but one thing that does jump out is obviously its DSP. Now these are super heterodyne transceivers. I think it's double conversion and the demodulation is done digitally, so hence the digital signal processing. Regarding the transmission, the modulation is achieved digitally, DSP. It just basically creates an intermediate frequency. It's fixed, then it goes through an IF food chain, gets mixed up, and ultimately comes out of the SO239 socket on the back and onto the antenna. Yeah, it's pretty standard stuff. So without any further ado, let's get into the repair, and we'll see what's occurring. So first thing I'm doing is I'm testing the receiver. So we hooked up to this test set at the back here. This is Marconi 2955. They're getting on, but it's still very useful for diagnosing and testing radio equipment. So yeah, we're injecting minus 118 dBm at 14.3 megahertz. Obviously we're set to FM, and as you can hear, the receivers, it's quite good. It's receiving it. That's good. I'm not doing a signal to noise test, but I can tell just by ear that that's working well. So next thing I'm going to do is put this into transmission mode. This is the test set, of course. I put that on there. Turn that volume down a bit, and then key up. Now, this is a good test. We can see, the radio is responding to the PTT being pressed, hence the TX light on. So that's good. We know it's switching. But if we look on the test set, you can see that it's not producing any power or anything of any value. Okay. So the next thing I'm going to do is have a look at how much current this thing's drawing when we put it into transmission mode. It's always a good test. Okay, so now I have got my multimeter. I'm actually connecting it in series with the there's the power cord coming from the power supply, which is feeding the radio. And what I'm doing, I'm set to DC amps, and I'm just going to be reading the current being drawn by the radio. So we're in receive, and we're just below an amp, there. So it's sort of 900 plus milliamps. And if we key up, it's pulling about 4.1 amps. Now, word of caution, if you're doing this, I just, I know it's not drawing a lot of current, but I just wanted to do this just to show you. But, these radios, it's 100 watts, so, they'll draw like 25 amps or something, and this is only rated for 10 amps. So if you put a meter like this in line with it, you're liable to blow the meter. Now, they are fused. But even so, if you blow the fuse, they're a real pain in the rear. You want to take it apart, change the thing, and obviously you can damage them. What I need to do, I've got a switch mode power supply. What I need to do is put it into a case with a decent meter on there. But if we key up, that's giving us 4.1 amps. Oh, incidentally, yeah, the RF set to 50%, and we can do that on here. Hold that in, and then if I press this, yeah, we're at 50% power. So what that's telling me is that there's DC switching going on, but it appears, let's get rid of this, but it appears that we haven't got any RF. Now, the increase is going up by, from 1 amp to 4, I'll say it's increasing by 3 amps. Now, that could just simply be the bias, because the PA's got biasing in there, and it's just putting it into transmission mode, which, to be honest, is actually a good sign, because I'm sort of thinking that the PA is okay. Normally if they start drawing excessive current, or it doesn't change when you key up, there's maybe something wrong with the PA. You know, it could be a switching problem, it could be transistors, it could be a whole host of things, but for me that is okay. So yeah, okay, let's do one more test on it before we get it apart. Okay, so we're going to do one final test before we get into it. So what I've got here is just another radio. It could be anything. I'm just using a receiver. We set to 14.3, set to FM, and I've just got a bit of wire hanging out the back of the radio of this icon I've got here. So when I key up, this is not seeing anything. It really. Now, if the PA was blown, I'd still expect to be able to receive something on the frequency. Just it's a proximity, close proximity, you get something. We're getting absolutely zippo. So what this is telling me is that for some reason, it doesn't appear that on the transmission path inside this radio, the the final product is not getting mixed up, because generally you would see something there. So from the test, we've concluded that obviously we did an amp test. By the way, yeah, it was pulling 1 amp on receive. That's quite normal. 3 amps on transmit, this was pulling, 4 amps with a 3 amp increase. Yeah, that's about right for the PA. So I make an assumption that the PA is most probably okay. We know it's receiving, and we know we're not receiving anything close proximity. So this isn't mixing up it's not mixing up the TXIF. Now where exactly that is, I don't know, but that's where we got to dive into the schematics. Okay, so this is the technical supplement. Well, it's basically a service manual. This is for the 450, and we've obviously got a 450D. Now, I don't think there's too much difference in them. Basically, I think the 450D has the option tuner unit built in, and I think most of all, it's had a facelift on the D. But apart from that, I think it's pretty much the same. It looks the same. So if there is any major differences, I'm sure we'll come across it. So if we come down, we have a quick look at the specifications. 30 kilohertz to 56 megahertz. Okay, and I'd said 54, I think, but yeah, it's got an even bigger range than I thought. And if we look here, we've got RX signal. This is power consumption, basically. So it's saying 1.5 amps, if I can highlight that. Yeah, 1.5 amps in receive. We were seeing about an amp, or just slightly below an amp. TX mode 22 amps. Okay, yeah, we haven't got any RF present by the looks of it, so we're just seeing what the bias idle currents are on the PA, I guess. So if we take a look down, we can have a look at the block diagram. Okay, so this is the block diagram of the PA unit. It's the RF power amplifier, and if we look, you can see these broken lines, which basically means this is the transmitter path, and the solid lines represent the receive path. It can be a bit confusing because the actual boards are denoted by a broken line as well. Okay, so this is the PA. It's very straightforward. What we have here, we've got a section in here. We've got a tuner unit. We've got a receive path here, which goes down and back. So this must be some kind of switch, even RX-TX switch or TX-RX switch. And also we've got this section here, which is quite simply the power amplifiers. So we've got an attenuator as we come in. We've got, they're like it's a Mitsubishi suite of RF power devices in the PA, and it just literally amplifies the signal. But this is what I was looking at here. So it goes final bias, drive bias, and pre-drive bias. Now basically what these are doing via these resistors, when you actually key the mic, a voltage will switch on at these points, and what it will do, it'll actually switch on these devices, or semi-switch them on. What they want to do is bias them so that they're in a reasonably linear state, so we keep our transmissions nice and clean. But when we key the mic, it switches it on, and that's what that current draw was, that when we key the mic. So I have a feeling that this section is all okay, and that's where our signals, our transmission signals, actually hit the PA board or PA unit. This is normally on a coaxial type connector, so you can unplug it and put it on a scope. We can actually see what's there, but I suspect we've got nothing, simply because when we did the proximity test with the other receiver, we couldn't hear anything. There was no signal there. So what I'm going to do, let's just follow this down. Let's start at source, and we'll go through the signal path for the transmission. If I can find it, yes, I think I found it. Here it is. We've got a CPU. Now, this is most likely it won't be a CPU as such. It'll have a CPU in it. It's a microcontroller. And what this is doing is controlling this DSP unit, which is dedicated to performing digital signal processing. And how it does this, it gets the information for the receive and transmit. Well, it sends the information for transmission down this way. As you can see, these are bi-directional points, and when it receives, it comes in at this point. Now they're using this codec IC, which is a digital to analog, analog to digital converter, and it breaks off into two portions. So we've got two functions here. We've basically got the receive function, as we can see, this is the unbroken line. So the receive signals come up here into the codec, and the transmission signals come away from here out the codec and go along here. Now this is an IF, and it's called IFI and IFQ, and you can see it says in, which is the receiver, out, which is for the transmitter. Now what's happening is the audio signals, your voice or whatever you're trying to modulate, whether it be data, the modulation's done digitally at this point, and what it's doing is it's creating I and Q. Now this is quadrature, and I simply means in phase, and Q means quadrature. So you're 90 degrees out of phase with the in phase. Now that probably doesn't tell you a lot, but from adjusting the amplitude and the phase shift on I and Q, you can actually generate some complex waveforms, and this is how it does it. I'm not going to go right into it, but there's plenty of people on YouTube who explain how this works. There's a lot to do with SDR. Basically works on a lot of SDR works on these principles. So what we're primarily interested in is, this is the starting point. So we want to see if these I and Q signals are present. And if we follow it down, comes off here, goes onto another board. Let's go up here. Okay, let's bring this across, and then we come up to here. So these are IQ signals, and basically what it does, it goes into this unit here. Now this is a quadrature modulator and demodulator. In this, in this state, it's only being used as a modulator, but if you look down here, there's another IC as well, which is exactly the same number, which is doing demodulation. So from the I&Q signals, we can actually create an RF signal because it mixes with the second LO. Now we know the second LO is present because it's receiving. So I think, we need to start from here and start working our way back up the transmitter. And what this creates is, this creates IF, and what the frequency will be is easy to work out because if you follow this along, we've just got a voltage controlled amp here, which is from a thermistor. This must be some temperature control, and this line carries on, comes down to this unit here, which is an RX-TX switch. That's just simply a diode pack. It's a dual pack common cathode diode, and it's designed as RF for RF switching. And basically, what it'll do, it'll switch paths for when we're in transmission and receiving and receive, and it just basically sends the signals through this crystal filter. Because of course the crystal filter is shared between the receive and transmit, and then all the switching does is it'll just switch the path through. It's like points on a train, on a railroad track, So then we come off, we've got some more switching. So again, as you can see, you've got a full line here, which is the receive, and then our broken line comes away, which is our transmission path. So we know this crystal filter's working because we're receiving. So we can make quite a few assumptions here. And we know our IF is 67.899 megs. It has to be, or it won't get through that filter because that filter is fixed. And then if we come along, the signal comes up here. And we've got another voltage controlled amplifier, which is being controlled by the ALC. But the ALC, it comes in here, we've got a mixer. Now that mixes up with the first LO, and this will give us our fundamental, this will give us our product, our final product. Now there's a bit of work to go through, as you can see, but this first LO is variable. This is what tunes. This is how we tune the radio. So it's the same in receive and and transmit, exactly the same. We know the first LO is present. We know it is because it's receiving. So we come out of there, we've got some attenuation, we've got a low pass filter, and more voltage controlled amplifiers, TGC, I'm not quite sure what that is. Then comes out of there into this TX switch, and it's an amplifier, so you can control it there. But I suspect, if there was problems along here, we'd still be able to hear it with the receiver with the close proximity. Now we'll just follow it through. We've got another TX switch here because again, it's sharing. This is a bandpass filter. So this is basically the receiver front end bandpass filter array. So there'll be quite a number of filters here. And there's a controller that controls, the microcontrollers within the radio will switch the correct band in. And, this is to remove harmonics and all the nasties. So we've got a clean signal. We have to have a clean signal. So that's, going into that PA, because whatever goes into that PA, it's going to amplify it. So this takes out the harmonics. It's been cleverly designed so that the harmonic frequencies, you know, they don't overlap or can actually appear within each one of the filters. We'll probably explain that a bit clearer later on. And yeah, another switch, surprise, surprise. And we've got another amplifier here, which again, it says amplifier and it's controlled at this point. So amp control, and where's this coming from? We've got a TX inhibit and send. Now if the TX inhibit was on, yeah, happy days. We'd still hear close proximity, a mixed up signal. We're getting nothing. So I don't reckon we've got a signal here. I reckon all this is okay. And we've got another attenuator, and then this goes off up to the power amplifier. So what do we need to test? Well, I want to take a look around this crystal filter, if possible. I want to look around here. I want to have a look and see if we've got our 67.899 megs when we key the mic, and see if that's there. If it is, I'd like to then have a look here to make sure that it's at this point and it's mixing up with the first hello. And if for any reason it's not at this crystal filter, we're going to have to look back. You know, we can look back at this. We can see if our I and Q signals are there. We can actually look at those on the oscilloscope, and we should be able to see the phase, you know, difference between I and Q on a dead carrier, which I imagine will just be 90 degrees. Yeah, we should be able to see that, and we should be able to see the second LO, make sure it's there and it's present and it's correct. Okay, so we've got the radio part. This is the top side. Now, this is the PA section, as we spoke about before. Obviously, we've got a pre-driver, two drivers where it just goes balanced onto the finals, and then we've got this transformer here, which is a combiner, so it's taken double-ended into single-ended, passes through here and goes into this section here, which is the low-pass filter. And this is an array, so depending on which band we're on, a relay or a pair of relays will switch in, and it'll let the signals pass. It comes out here and then it goes underneath. There's a little hole here, which then goes on to the antenna tuner and then comes back up with the looks of it, and then comes out the antenna socket here at the back. So our final product, RF signals, will come up here and basically plugs in here. So that is a coaxial connector. So if I unplug that, what I'm going to do is put the scope on this and see what we've got. We'll key up and see what we've got. We're still set to 14.3 megahertz and we set to FM. So we've now got the scope connected. You know, I can keep the mic, and if we move this up carefully, again, if I key up, we're not getting anything. We set at about, I think it's about 200 millivolts per division. We should be seeing a strong signal there. This is a 100 meg scope, and normally what comes up onto those PA boards is typically on radios around, it can be anything between like -10 to 0 dBm, which, you know, that should give us full power on the output. But obviously we're looking at the RF input to the PA here, and as I suspected, we've got naffle, Your Honour. Okay, so this is the underside of the board. Now we've got our demodulator. I see it's a quadrature demodulator. This basically takes the IF signals from the receiver, turns them into a I and Q quadrature baseband signal, and then that in turn feeds the codec, which then goes on to feed the DSP, and all the magic happens in there. So that's for the receiver, and this IC here is the modulator. Now this is taking the I and Q signal baseband that's being generated by the codec, and then it converts it into an IF frequency. So the modulated, obviously the voice or whatever it is you're modulating is represented by I and Q, and then this creates the IF, and it does it by mixing with the second LO. Now, as I said before, these are the same ICs. They've decided to use two rather than piping them around. Yeah, it makes complete sense. They must have looked at it for the component count and thought, well, it's probably better we use two. But one of these ICs is capable of doing both jobs. Okay, so what do we want to do? Well, I want to have a look at the IF output of this, and we know this should be around 67 megs. Also, we can have a look at the local oscillator and the I and the Q baseband signals coming from the codec. So, yeah, let's get this connected up and see what we've got. Okay, so I've brought the scope down so that you can see the display. I'm doing a bit of jiggery pokery with the focus, apologies. So what we're going to do is look at the output of the modulator IC. So it's pins 6 and 7. They're joined together, and if I key up, we're getting quite a waveform there, but the problem is it's just shy of 24 kilohertz. Now I'd expect to be seeing a signal of around 67 megahertz or signals, and I'll explain that as we go on. So something appears to be wrong there, and if we look at our quadrature signals, okay, so that's pin 1, which is the input of the in-phase signal from the codec, and this is pin 3, which is the quadrature. And as you can see, as I'm talking, you can see it modulating, so it's picking up from the mic. Okay, I think we need to look at the circuit diagram. There's something very wrong here. As I say, the IF, we should be seeing around about 67 megahertz. So let's look at the circuit diagram. Also have a look at the data sheet for this IC. Okay, so this is the schematic. It's the RF-IF unit, and that was the board on the underside that we were looking at. Now, this is obviously from the technical supplement. We've got these ICs here. So this is our DMOD IC, and this is our mod IC. Now, this is the one we're interested in. Now, we saw that we had signals here, I and Q, and they were about 24 kilohertz, and they obviously go in on pin 1 and pin 3 of the IC. So the inputs and the outputs are, well, the output is from pin 6 and pin 7. As you can see, they're actually joined together here. And this goes off to this amplifier, and in turn goes up here via a switch, and then goes off into our crystal filter. So the 67 megs isn't there. All we're seeing on the output, which one is it? It's here. All we're seeing is just shy, about 24 kilohertz. Okay, now you're probably screaming at me at the moment saying, hang on a minute, you've not tested to see if the second LO's there. Well, I know it's there because if we look, this is the second LO here, which is at 135.75 megahertz. And that, and if we follow it along, you see it just tees off. We've got a coupling, an AC coupling capacitor that goes up to feed the DMOD. We know it's demodding, so we know it's there. And we've got down here, we've got a little capacitor, and it goes in on pin 13. Now, my oscilloscope is only got a bandwidth of up to 100 megahertz. However, I will test this. We'll test it. but we'll have to use a spectrum analyzer, and it's quite, the nice people at Yaesu have given us a bit of information, so we're expecting to see minus 16 dBm at this point, and there's a little test point there. It's right by the D mod IC, which we'll have a look at in a second. Okay, so let's just have a look at the data sheet. Now, this is the data sheet for the unit. They're given example circuits, and you know, it's an RF2713 device. I've forgotten who makes it. So in the example circuit, again, we can see I and Q, which is on pin 1, and Q is on pin 3, exactly where we were testing, so it's exactly the same. And the output, and as we can see on pin 6 and 7, you know, they're joined together, and there's a little pull-up resistor to VCC. Now that's another thing we need to test, make sure the voltage is there. So we should be seeing 5 volts according to the schematic. I'm sure that's there, but we'll test it anyway. And this is our local oscillator, or it's our second LO input that goes in here. Now if you noticed on pin 13 where it goes into this, it's called a quad divide by 2. So let's just go back to the schematic. So we have got a frequency here of 135.75. So if we pull the calculator up, so we go 135.75. We divide that by 2. Okay. And what we want to do is add 24 kilohertz. So 0.024. There we go. Okay, so 67,899, and funnily enough, that's exactly the same frequency as the crystal filter. Now remember, the crystal filter is a bandpass filter. I don't know what the bandwidth on this is. I don't think it's that narrow. These don't work, this type of system doesn't work the same way as a conventional older style super het. Obviously this is the bandwidth done by the DSP, so I imagine this is reasonably wide. Now I mentioned signal, so if we just go back to the schematic again, let's just, not the schematic, let's have a look at here. So we've got these mixers here. So if we just zoom in a bit on that. Okay, so we've got our, apologies for the phone keep pinging, I seem to be very popular at the moment. So we've got these baseband signals that are coming in, they go into the mixers, and that mixes up with the LO. The LO is divided by 2. So essentially what we should be getting, I imagine, is 2 frequencies on the IF out. There should be 2 frequencies. There should be a sum and difference. So from the LO divided by 2, we should have plus 24 kilohertz, and then we should have minus 24 kilohertz. So what we'll do, we'll put the spectrum analyzer on here and have a look at this in a little bit more detail. Also, what we can do, we'll just see what signals are present there, and what we can do, we can actually put 2 probes on the I and Q to make sure that we've got a 90-degree phase shift from the in phase to the quadrature. I'm sure it's there and I'm sure that's working, but let's just test it. And again, we'll just test that VCC, make sure we've got our 5 volts. And if that's all working, I can't see anything else that could really be the issue here. We could probably check some of these capacitors, but everything seems to be leaning towards this IC. I would say that this bad boy is the culprit. Okay, so we'll do some more tests and let's see what we've got. Okay, so as you can see, I've got 2 probes attached. I've just literally soldered some wires on. Now we're picking up the I and Q, And if we key up, okay, so you can actually see what I'm talking. The yellow trace is the in phase, and the purple trace is the quadrature. Now you can see the quadrature there's a 90-degree phase shift here. It looks to me like it's lagging the in phase, or is it the other way around? I don't know, but that looks okay. That's what I'd expect to see. So the codec's producing the right signals, and you can actually see 1, 2, 3. You can see it's modulating. Okay, so I'm going to check to see if we're getting the voltage to the IC. Now pin 14 is the VCC, and we're supposed to be seeing 5 volts, 4.84. That seems fine. So we've got the spectrum analyzer set up. I've got a center frequency of the second LO, which is 135.75 megahertz. And if we go on the test point, yeah, you can see that's there. I've actually got a marker on it, and that is on the money. And if we actually look at the pin, I believe it's pin 13, because I just want to make sure that capacitor, yeah. So yeah, that's going into the IC. So the local oscillators there. This is obviously using a oscilloscope probe's a bit dirty, fast and dirty, but it's not good for taking accurate measurements, but I don't need to. I just want an indication. That's what we've got. Okay, so now I've just set the center frequency on the spectrum analyzer to the IF frequency, which is 67.899. That's the same as the crystal filter. And if I look on pin 6 and 7, we put this on here, key up, you've got absolutely nothing. Now, obviously before we were getting the 24 kilohertz, this is not going to see that, because obviously we're set up at around at 67 megs, and I've only got a 1 meg span, but as you can see, there's nothing. What I'd expect to see is 2 signals there. Obviously the LO divided by 2, and then plus 24 and minus 24 kilohertz. Okay, so we've checked make sure the LO is there. It's going into the IC, the second LO. We know we're getting our quadrature signals. The amplitude of them, yeah, it looks okay. I mean, I don't actually know what the correct levels are, but we'd be getting something, and on the output, we're certainly not seeing anything around the IF frequency. So it just seems we're getting the 24 kilohertz out, which just looks like some kind of bleed through from the mixers. I don't know what kind of mixers are in here, but obviously a lot of mixers are good at suppressing the first order products, like double balance mixers are good at that. So they sort of take the origin signals and the LO. It reduces the pass through. I have no idea what would happen on this. So yeah, so it's time to change this IC. Now I do have one, so I think we're gonna have to get out the hot air, and we'll get this thing replaced. I'm pretty confident that's what the problem is. It's a strange fault. Yeah, why has it blown? Why has it gone? You'll probably see some soldering around here. That's me when I was playing around tacking on wires so that we could have a look at the quadrature. Okay, let's get this thing out and let's see what happens when we replace it. Okay, so we have replaced the IC. This is the old one, the one I've removed. Obviously put a new one in there. And these are actually quite difficult to get. This came from China. It was quite a good seller apparently, so we came, and yeah, it's working no problems. So if we key up now, you can actually see it's producing power. Now I have had a quick check of it. I will go through it, but yeah, that's working. So I actually removed the old one with hot air. I basically used I just made a shield out of foil copper. It's just so I didn't disturb the other components. And this is, I've just got one of these Atom hot air rework stations, and then I resoldered the the new one in. I just put it in by hand, so just carefully put it in there. So that's it. It seems to be working. Okay, well, if you stuck with the video this far, I'd say thanks for watching. I hope you found this interesting or of help. One thing I will say, if you're repairing radio equipment, a lot of people ask me, what they think's wrong with their equipment. Now, you've got to do fault finding, and you've got to, you can see the benefit of it. A lot of people just seem to shotgun components into, radio equipment because they've seen somebody else do it. So if you've got a similar fault, doesn't mean that this is the problem, okay? So, the classic one is capacitors. People have, shotgun capacitors into equipment in the hope that it starts working. But you need to fault find. Any tech will tell you that. But okay, no worries. Well, I hope you enjoyed it, and we'll see you in the next video.